So, good evening. I'm going to give a talk on hardware anti-tamper, why and how. My name is Ryan Lackey. I work at a company called CloudFlare, and I'm on Twitter as @Octal, so you can follow me. I'll post the URL to the slides on there. For some reason, it's not working right now. So, I've been involved in this for a pretty long time. Back in the 90s, when I was like 10, 12 years old, I was really interested in crypto server deployments because of the cypherpunks mailing list. We were discussing stuff like blacknets, where you could anonymously trade information, systems that would persistently store things, all sorts of other crazy stuff, a lot of eCache. It was pretty cool. The problem was, even back then, it was pretty obvious that if you're building secure software systems, you need to have some sort of secure hardware substrate to run them on, or advanced crypto that we didn't have back then. Then I learned about HSMs, the hardware security modules. I was like in college, and I bought a lot of this stuff on eBay, and it was fun to play with. I did offshore eCache stuff. I moved during the ITAR days. There was crypto was illegal to export from the US, or you couldn't export it without a huge permit process. So I moved to this little Caribbean island and worked on an anonymous crypto library with non-US citizens, and I would write an academic paper on like how to implement it, which I could publish to the internet. They could download it, implement it, and it would be pretty cool. So there was no legal negatives to that. So it was pretty interesting. It was just really slow. Then I ran this offshore data haven thing in the North Sea from 2000 to 2002, where we set up on a World War II anti-aircraft platform. It didn't go so well. The .com collapse happened in the middle of it, so all sorts of crazy stuff. Then I worked in RFID and NFC payments for a little while, and then I got into I met some random people on LiveJournal, which is like this blogging site from back in the day, and moved to Iraq to like help them set up an ISP. And I spent the next 6 years working in Iraq and Afghanistan doing networking stuff, which was interesting, but definitely not going back. And then I started a startup called CryptoSeal, which was in the trusted computing space, so I got to work with a lot of this technology, and CloudFlare bought my company back in June of this year. So it's pretty much what I've done. So I've worked on this stuff in a variety of contexts, as a hobby, as a commercial thing, for a while. So the idea here is anti-tamper, but you really have to start with like, what is tampering? It's intentional malfunction or sabotage by people with access. It could be either people who have legitimate access, users trying to exceed their authorized privilege, or it could be people who are to gain access to something without permission and then try to make it do things that it shouldn't do. It's really a foundational security technology. I mean, it's like a layer cake, and if you take away the table that the layer cake is on top of, it all crashes to the ground. So it's a pretty important thing. The problem is it's sort of at the intersection of hardware, software, firmware, a bunch of different fields, a bunch of other stuff that all don't really work that great on their own, and working together they really don't work very well. So it's a pretty tricky thing, and there's not really like a strong academic progression of skills that people go into from this. I've seen people from like an art background, from a computer science background, from a math background, everything else become like really good at it. So it's a pretty diverse field. So anti-tamper itself is sort of broken into a few categories of things. There's straight tamper resistance, there's tamper evidence, tamper detection, and tamper response, and they really mean different things. I'll go over some examples of them. It's probably the easiest way to go over that. But the issue is that these are all fairly difficult to work with. All this stuff's difficult to work with. So in general, you try to protect only certain parts of your system. Nobody really does general tamper resistance for their whole system end to end right now. It's fairly difficult. So you just find the core parts of your application and protect those. It'd be great as the stuff gets better to protect more of your application, but that's not really the easiest thing to do right now. So you've got systems that are tamper resistant. So there's physical systems and there's electronic systems. We're going to start with the physical systems. Physical systems that are tamper resistant are themselves difficult to tamper with. They do this because they use materials that are difficult to work with. They use things that are non-standard. So just using a different screw pattern for the enclosure of your iPhone is a part of Apple's anti-tamper strategy. It's also part of their warranty strategy and a bunch of other stuff, but just making stuff inaccessible or difficult to access. And locks are a low-level anti-tamper technology that's designed to be tamper resistant. The other systems are those that are tamper evident. So in the case of an ID, you want it to be difficult for somebody to modify the ID without being caught. You don't really care that somebody can go home and paste a photo of themselves on top of somebody else's ID, you do care that anybody verifying that ID can tell that someone's done that. And then you have systems like cargo containers and everything else where you want to make sure that people do audits at various periods, like customs and other people do inspections, in order to make sure that the system hasn't been surreptitiously entered in between those inspections. You don't necessarily know what's in the container when it arrives. You just match it up to something else, but you want to make sure that after you check it, you don't have to check it again if the seals are intact. So it's a tamper evidence system. Once you move into the more electronic world, you have systems that can detect tampering, so tamper detection. The idea is that the electronic circuits on the system can tell when something has happened and at least behave slightly different. And then the highest level would be tamper responding systems that can both tell that they're being responded with and take fairly advanced actions. HSMs being a pretty good example of that. And there's thing that progression also becomes more difficult. Like all of this stuff is a spectrum, and some, like doing a really, really great tamper-resistant system, of course, will prevent all the other stuff, but it's very difficult to build something that's going to stand up to even a few seconds with great tools. So you have to use a combination of these technologies and figure out which things you actually need to protect and what you're protecting. But as I said, there's the physical systems and the electronic systems. Of course, physical stuff has been around. Physical tamper evidence has been around for forever, for a very, very long time. Coins, when you have a coin like a quarter, a US quarter, on the outside, the milling on the outside is there so that you can't shave the coin, because coins used to be made of precious metals and the weight of the coin mattered. So the reading on the edge would make it obvious to a merchant when they accept a coin that somebody has shaved off little bits of precious metal from the coin. Now that the coins are made of like zinc and copper, it doesn't really matter, but it's an example of a physical tamper evidence technology. Then you've got electronic systems that are protected by large-scale physical anti-tamper. You've got like all your network gear and everything else sitting in a locked cage at a data center. Then you have electronic systems that have these integrated anti-tamper systems, like the Smartcards and the HSMs that I showed. And then the unfortunate thing is that physical stuff is getting really, really hard to protect. It's really easy to counterfeit things, like physical objects counterfeit things. It's really easy to get tools that are really amazing to cut through metal and do all sorts of other stuff. So I actually don't believe pure physical tamper evidence / tamper resistance technology is going to get any better than it is relative to the attackers. I think it's on a long downward trend. So things are going to move toward more electronic seals and active seals. There's other reasons why you want to do that. And like in the inventory control world, you don't want to have your guy go and walk to every single one of your containers and check the integrity of the seal, check the serial number and everything else each time. So people want to do that with RFID. So it's the stuff's moving to electronic anyway. There's another whole category of why electronics need anti-tamper. Which is pretty interesting. Fundamentally, it all boils down to when you have equipment and you put it in someone else's control. In the case of the consumer space, it's really obvious. The SIMs that are actually the property of your network operator in your smartphone are an example of a smart card, and those are an anti-tamper technology. And then satellite TV is a great example, and I'll go into that in a little bit. Any system where there's a risk of theft or capture, so lots of military systems, lots of systems that are being shipped around are worried about both being captured while they're in transit and then captured while they're in operation, and making sure that they can't do things that are not wanted. And then there's, in an organization, generally employees themselves do not own 100% of the organization. There's an agency issue where a single employee should not have full control over everything in an organization. And one of the fundamental principles of audit and security is to have dual person or multi-person control over important operations. And not all that stuff breaks down when your sysadmin has full root and access to the whole system and can do whatever. So implementing multi-party control, mandatory access control in organizations is another area where anti-tamper is used. And then cloud services are actually the thing that I think is why anti-tamper is the most interesting. In cloud services, you never see the servers you're working with. They're effectively virtualized, and you have to rely on them somehow. So it would be really nice if there were a way to know what your server is actually doing, what it can do, what it can't do remotely as the end user of an application. So I talked about smart cards, but we should go into quickly what smart cards are. They're basically a microprocessor in a small form factor, inexpensive, They're being used in a variety of systems. I mean, the cell phone systems are great. Transit systems use them widely. EMV, which is one of the new payment systems after Target and Home Depot, and it's been used in Europe for forever to do NFC RFID payments, use them. They're designed to be inexpensive devices that can be mass-produced and contain some credentials inside them that are secret and kept secret from whoever has physical possession of the device. So I can use the device to do certain things, but I can't extract the credential. And then I also mentioned HSMs, which are hardware security modules. They're like the super mega version of a smart card. They are generally a general purpose processor that's inside a secure envelope with its own battery backed up power source to operate for 5 or 10 years in backup mode, with much more expensive tamper responding technology, much more expensive tamper detection technology built into them. The cool thing is, so I bought a bunch of these on eBay. They're like 30 grand, and you can buy them as pools from banks for $200 or $300 usually, and about half of them work, and about 10% of them are loaded with people's keys. So it's it's pretty fun. The fun thing is to cut them apart and see how they're made, which I'm not going to do with a $30,000 device, but I will occasionally do with the $200 device. They have this Gore-Tex, or WL Gore, the company that makes the Gore-Tex jackets, or the fabric that's used in the Gore-Tex jackets, makes a special tamper-responding membrane fabric that's used inside these things. So they've got like a metal shell, and they have this weird cloth fabric that has a bunch of little wires in it. And if you cut the fabric, or if you modify the fabric in any way, it does something to a sensor. The other cool thing is these HSMs have temperature sensors, so one of the attacks on smart cards and everything else is moving them outside of their approved power range, and you can freeze them so they have longer memory. You can heat them up so they glitch. Usually going colder is better. The HSMs put a temperature sensor inside, a little cheap temperature sensor, usually a couple of them. And IBM, so the interesting story is IBM made the 4758, which is the first one I ever worked with, which is in like 98. And I think they were late to ship them to their customers because they had like a deadline they had to meet for a quarterly thing. And they were going to ground ship them all, and they decided at the last minute to airship them. So they airshipped all of these 30,000, well, they were actually $3 grand, but they were very expensive devices to all their customers. And every single one of them arrived bricked, and like permanently bricked, because the cargo hold on an airliner for freight gets below the negative temperature for these things. So they had to start shipping them out with those like ice packs that you use in your freezer, not frozen, attached to them, so they have enough thermal mass that it'll take a lot of time for that thing to freeze, like raise the specific heat of the device. So it'll take a while for that thing to freeze, and that sort of solved that problem for them. But they're a pain to work with, they're difficult, and they're expensive. So satellite TV is actually one of the most interesting areas, because I think it's always sort of silly to talk about attacks and defense as like separate things. I think these things co-evolve. And with satellite TV, there was an exceptionally awesome community of people attacking satellite TV versus people that were in the building the satellite TV. I work with somebody from EchoStar now, and the whole like going after pirates thing. There's a couple books that are really good about it. It was a really exciting game. So they built these smart cards, and they put them into all of the consumer sites. They have the hard problem of everybody who wants to attack them has a copy of the device and can get them for like $10 when they get a new card. So, and what happened was Canada would not allow these devices to be sold, or some sort of marketing reason. There was no ability to legally purchase satellite TV in Canada, but Canada has a lot of really good software engineers and hardware engineers and hackers that wanted to watch TV. So there was a market where it was like quasi-legal to go after attacking these things, and a lot of people who were very resourced and very motivated to do it. And people would pay for free TV, back when TV cost a lot of money. So the world, it was like a cat and mouse game of probably for 20 years of coming up with better encryption systems and key management systems for the satellite TV world, and then people attacking them. And I think Chris Ternovsky, who's probably the best non-government person for attacking integrated circuits, and now works at IOActive. He had a company, FlyLogic, for a while, came from that world, and it does crazy stuff with like a focused ion beam workstation, which is like a $500,000 device to modify how the chip works and all sorts of other stuff. Doing crazy physical attacks on chips to defeat their tamper response technology. Then there's the X99 pin pads that people use that are supposed to be tamper evident and tamper responding, but in practice aren't, or a lot of them aren't, or those ones were not deployed, so you end up with people skimming off of these devices. And then there's, of course, military hardware that has all this stuff built into it. But fundamentally, the big thing about all this anti-tamper technology is what happened in the late 90s with DRM. It was sort of this exciting period where Intel and Microsoft got together and wanted to build a DRM system to allow video content to be downloaded on the internet and securely decrypted on the client devices, which was sort of one of the principles of like computing is you're allowed to run whatever code you want on your own computer if you own the hardware, and that would have totally broken that whole principle. And everybody, a very large number of people within the tech community were thinking this was like the end of the world, and there was a crazy fight against it, such that Intel and Microsoft, these huge companies that had a huge consumer-centric business and were really, really worried about losing that business, decided to back away from this stuff because it was so toxic. Trying to expand this tiny bit of a business, it might lose them the bigger consumer business. But they put a lot of effort into building what later became the Trusted Computing Group, TPMs, a bunch of things on PCs that didn't really die. They just sort of went in the background and were being developed. And they refocused toward uses other than DRM on the enterprise side, the Intel vPro technology. On the server side, Intel TXT are pretty much direct extensions of the Microsoft Palladium, Intel stuff from back then. So I remember all this happening, and I was super anti-DRM, anti-trusted computing, and I talked to a bunch of my friends who were like cyberpunks about how this stuff was horrible, and sort of like moved away from it and did other stuff. And then I went back a few years ago, I think in like 2008, 2009, I was talking to like the people that were anti this stuff, like why do they think it was so horrible? Now they think it's actually okay. There's two fundamental changes that have happened. One, the mobile phone, and two, the cloud. We've pretty much accepted all these restrictions on what software we can run on our own devices. Like we go out and we pay like $900 for an iPhone and you can't actually run your own code on it. So we pretty much gave up that whole fight. And then the cloud, where you never really have physical custody of your machine, you're not going to lose anything by losing the ability to do whatever on your physical thing. So there's really no downside to implementing this technology now, only upside. From a rights perspective, you've already given up like all the rights that this thing would take away from you. And then there's the other side is that the tools to defeat the alternatives to this are getting so crazy. Like 3D printing, like I can take the most secure lock, and almost always I can destroy the lock in order to gain access to something. Part of using a lock as a tamper indicator is that I can't destroy the lock, or as tamper evidence, is that I can't destroy the lock and replace it with one that's exactly identical. It's not really true. I can actually go out and I can etch the serial numbers on all the components now. I can make replacement components, all sorts of other stuff pretty simply with equipment that I could fit in a van and take to a job site. So there's that. And then the open source world of like people at DEF CON at Tamper Village hacking on this stuff has gotten pretty good at defeating almost all the commercial anti-tamper stuff. There's a group at Department of Energy. So I know a little bit about the government stuff. I've done a little bit of government stuff, but it's never been in this tamper world. But I know people from the Department of Energy who are part of this group called the Vulnerability Assessment Team, who did a lot of work on seals. A lot of the stuff was open back in the 90s, and they took it down after 9/11, but I have like lots of archives of it. It's pretty depressing how bad the physical seals that they're evaluating are. The mean time to defeat these things is really, really low. The cost to defeat them is so low. And like the best seals they were able to come up with were like 90 minutes to defeat. So it's not like you get that much better. Most of these are through various forms of attack. Like the high end, you can do counterfeiting attacks. So there's that. And then there's the fundamental principle of like users are lazy. So anything that really takes a lot of work for the users to do, which a lot of the tamper evidence does because you have to have somebody go and physically inspect everything, really doesn't work in practice. You just have people click through. It's easier to skip doing a walk around and check on every serial number on devices that are deployed all over the world than it is to justify clicking through, and people have no problem with either. So there's that. So I've been looking at this problem for a couple of years. Last year I worked with Eric Michaud, who worked at DOE for a while, on coming up with a way to do a cheap passive seal that could be verified with your iPhone. It's pretty cool, inexpensive, everything else, but it requires a user's physical presence to do stuff. I mean, I'll just quickly show what it is. It's a way to do blink analysis on devices using an iPhone. So you can go, So there's a slight change between the two images, which isn't apparent when you just slowly look at them, but when you rapidly move them is. I don't know how I have this set up, so it's there. But yeah, one of the screws is moved. It's really easy to do that analysis with a machine, so we use OpenCV and we can do it. The idea was that you would take the image, send it off to a trusted server, do the comparison, and get back a Kerberos ticket or other short-lived credential. It's pretty cool. We found a cheap way to do it using nail polish and like pearlescent or candy paint, and putting it over the sensitive parts of it. So we ended up with effectively remote verifiable seals. This is kind of cool for client devices, but not actually very relevant for servers. On servers, there's the conventional HSM solution, and there's lots of other solutions. I mean, I think in the ideal world, we would just use HSMs because they're designed to do exactly what we want to do. They're tamper responding, but they're 30 grand. And there's another really, really serious problem with the HSM is the HSMs are made by 2 big organizations and like 2 or 3 smaller organizations. And if you're a bank or a government organization and you buy one, you'll probably get a good one. If you're like WikiLeaks and you try to buy an HSM from a manufacturer, or if you're like a Chinese startup or something and you try to buy one from a US company, the odds that one of those things is going to be tampered with is like, before you get it through interdiction, is like 95% or something. So they're really not viable. They're the ultimate black box. There's no way to really verify them without cutting them open. So they're not really too appealing for a lot of reasons. Plus, they're so it used to be that you'd use all these HSMs as crypto accelerators because they were faster than the general purpose PC. So like a 46 DX2 or something server couldn't do RSA very fast. It could do the 1024s at like maybe like 10 operations a second or something crazy like that. You could get silicon that would do it a lot faster. Now that's sort of swapped. The processors inside these HSMs are usually just ARMs, like pretty low-end ARMs, because they're worried about getting heat out of the container. And your PC has like a crazy Xeon or something that can do 4,000 operations per second. So your PC is much faster than the HSM, so there's no reason to buy them as accelerators. And they don't let you easily do the kind of other stuff you want to do. So a lot of people have these problems, and usually it's for very specific applications. ICANN and IANA, the people that are responsible for a lot of the DNS and number allocation, are working on DNSSEC, which I've been looking at myself. And one of the guys there is working on, so DNSSEC has a requirement for a credential that's inside the device, and it's inside their DNS server, and it's kind of exposed. So they are cost conscious, and they wanted a good solution. I came up with something that's like $100 to solve this. It's not produced in any scale or anything yet. Which is pretty interesting. It's one of the areas I looked at. Then there's things, the Yubico, like the little token things, have a UBHSM that's used to validate them on the server side, but it's used only for that operation. You can't use it for general purpose calculations. So you couldn't build like a general purpose tamper system with it. And then there's the TCG. So as I said, all that like DRM technology that people had been working on, that was so toxic that people like backed away from it and sort of tried to forget about it as much as they could. People kept developing, and in I think 2009, Intel came out with TXT, which is a combination of VTD, VTX, which are both virtualization extensions for DMA and virtualization, and then a few other technologies. AMD has exactly the same thing. ARM has something called TrustZone. So there's all this stuff that people have built. It's just really, really complicated. It's built from microcontrollers to start with, and they're attached to like the floppy bus on your computer, which is sort of crazy. So they're kind of a mess. And the TPMs themselves are not terribly tamper resistant. They're certainly resistant to software attack, but if you have physical access to them, they're like FIPS 140 level 2 or something, so you can pop them pretty easily. There's some cool technologies coming up that aren't out yet. So my startup, we were like hoping this thing would be ready, but it's not ready for another probably 2 years. Intel SGX, which lets you do all that crazy complicated TCG stuff, but in a very simple way, where each process can have a key that's assigned to the given process. All this cool stuff, but we just don't know when it'll ship, so it's kind of not really viable to do. And then people have built virtualization-based systems for this, so you could build a cloud system using this. There was a cool company called PrivateCore that Facebook bought about maybe a month and a half ago that had a hypervisor that ran entirely within the L1, L2, L3 cache of a Xeon processor, as long as you had a big Xeon processor. And the idea was that you can do DMA dumps using like a slot screamer or something else on main memory, but you cannot actually dump the cached memory on a processor. So effectively, because Intel CPUs are built in the latest crazy process, they're really a pain to reverse engineer. And they're also very difficult to reverse engineer like quickly. It would take you several hours to remove one from a data center and start doing analysis. So as long as you have ephemeral keys that are living inside this, you can do pretty cool stuff where, you know, the attacker is going to take 3 or 4 hours at least, probably actually several weeks to attack. So you can expire your keys every 6 hours, and if the server goes offline, then you rotate your keys. Unfortunately, they got bought by Facebook, I think, to build this stuff out for Facebook. I'm not really sure. But there was some open source background to what they were working on called Trevisor. So Tresor was sort of the first version of this, and then Trevisor, but none of it actually works. So they spent 2 years making it work, and it's a very interesting area for people to work on in open source. But there's that, and then there's a pure software solution to all this, which is probably better than any hardware solution. It's just really difficult to do. There are cryptographic systems that let you split keys across multiple locations and require that multiple servers cooperate to do something. But the general case is very slow. There are some recent advances in it, but it's still very, very slow and inefficient to do. There are very specific cases just specifically for signing and for certain other things that are very efficient. So people have talked about this being a very interesting area of research, but I'm not really like a great crypto mathematics person to come up with a new algorithm for this. So I'm hoping that somebody will do something in this area, but I'm just watching. There's some really obvious stuff you can do, like you can take a Raspberry Pi and put it in a box. You can make your box like arbitrarily tamper evident by putting a bunch of stickers on it and everything else. It's pretty cool. It actually is a reasonable solution. We looked at doing this for a variety of things. At least, at the very least, if you compromise your host computer and you've got a very well-defined interface, maybe a one-way interface talking to this little box, nothing you do on software on one system will compromise the other system. And the Raspberry Pi is actually a great platform to start with this on. The problem is it doesn't have ARM TrustZone, which is one of the elements you'd really want, which is present in a lot of the ARM processors for cell phones. So, for instance, Apple uses it for protecting Touch ID. It would be a nicer thing to extend that. But it's definitely a good area. There's a thing, CryptoStick. So there's all these smart cards that end up being put in readers and other form factors. People use them for key signing, but there's a problem. Like, I'm not really that interested in building this just for key management. Because if I build something that will sign arbitrary files the way a lot of the smart cards using like PKCS11 will, you just need to take that card and put it in something else and just ask it to sign another operation. I really want something that will do general purpose operations within the secure envelope and tell you that like this is being, so you can put your whole process inside it and do some checks to make sure that the operation should happen or shouldn't happen. But it's a cool device. Some other people working on SmartCard-HSMs, but they're still basically for key management. So, yeah, some basic principles. It'd be nice to be able to do arbitrary computation is the fundamental one. And all this stuff is about, just like tampering is doing things that you're not supposed to be able to do when you get access to a system. You need to build this whole architecture of access control and everything else on top of it. And the best way to do that is to use something that's pre-existing, because doing a lot of work there would be a pain. There have been attacks on HSMs. They've generally been software attacks. Like the hardware is attackable, but because they're so expensive, people don't put that much effort into doing open source attacks, and people who do private attacks probably like to keep their attacks private in those particular things because they're going after a specific target. But there have been public software vulnerabilities with the APIs and stuff they do. So all of your traditional software security stuff still applies. You just have a stronger substrate to run it on. And the feature that I really want for all this stuff for the cloud is remote attestation. I want to be able to tell an end user what code is running on the processor they're talking to and what the environment is so that it knows it can't store data in other places or whatever else. Because the holy grail would be you could build something that's sort of like EC2 or AWS EC2 that runs in some very hostile environment. And as long as you know this hardware is an intact piece of hardware and you can talk to it over some sort of secure channel, you can do something like a password checker, like send it your password and have it see how strong your password is and know that all it's doing is running those operations. There's no side effects. There's no data stored. That'd be a pretty crazy security model to try to build for, but it is the sort of the holy grail. So there's 3 options to this stuff. I think we could try to build an HSM much more cheaply, make it open source, let people verify it themselves, design systems that keep the most sensitive data far away from the attacker. So build something where the client is an untrusted client. And then there's layered systems that have like more forms of anti-tamper throughout the system, which is what the best people are doing right now. On the HSM world, there's really 2 options here. I've done a bunch of analysis. There's people that have good HSM designs that have worked on it in academic projects and various other things. It's like $250,000 to do. It would take about 2 or 3 years with a few people. it's pretty much within the Kickstarter range. I think we see people raising Kickstarters of like $5 million, totally within VC range. You could probably do them for about like $1,000 each. They'd be basically like a really, really high-end smart card or a really low-end server, and you can get them FIPS certified. So it's really like a two-year time. The problem is it would be a new development model, new application model, everything else for them. And even $1,000 is pretty expensive. So you need to find a vertical market for these things that really made a lot of sense, like password verification in a box or something like that. The other alternative would be making a really low end one, sort of like a smart card, but going up from that. And those are a lot cheaper to do. It's more just software on an existing smart card to start with, things like that. Totally within Kickstarter or even like a side project type range. And try to make them like $50, $100 each. I built this thing with Mark Rogers and that was building on stuff that Gruck had worked on and working with Gruck, Portal Travel Router, and we see that stuff that's in the like the $100 or less price range is a lot easier to work on because you don't need to worry about financing inventory and everything else. So it's pretty cool. So there's those, and I'm looking at those, and if people are interested in working on open source HSMs, I think it would be something the way sort of like Facebook does that open hardware or open connect platform thing. If somebody did the same thing for the HSM world, so sort of like an association of people working on it rather than a single company, it would be pretty interesting. The other solution would be remote keys. So I just worked on launching something that uses this, and this is sort of a general technology you can use in your various stuff. The idea being to keep your sensitive data outside of the risk environment. We built this thing called keyless SSL, which is basically like a network HSM, where in this case the user trusts themselves to hold their own keys, and the server is my company, and then the user doesn't trust us with the keys. So we built something where the private key operations happen on-premise with the user, and we use the symmetric operations. So there's a solution to that. There's network HSMs, which are basically HSMs inside a PC that are shared across a bunch of machines. So you can at least then centralize your keys in a single machine and have a bunch of front-end web servers that aren't themselves trusted as much. And then there's open source software like Tor and Mixmaster that depend on networks of machines where you don't trust any single one of them fully. And that's a pretty good solution. And the other cool thing is layered systems. So people have built these at various places. PirateBay just disclosed how they built theirs, which is pretty interesting. Twitter, Facebook, and Google, I've talked to a bunch of people there about how they build their key management infrastructure. Pretty much any large internet company, any large consumer company at least, goes this route. Large banking sites and things like that usually go the HSM route. I know a lot of the details about CloudFlare. I didn't really get permission to share them, so I'm putting them at the end. And then there's stuff with load balancers and there's open source solutions. So PirateBay is the cool one to talk about because they just announced it. They're using a bunch of cloud instances, and the idea is that they have a bunch of lightweight throwaway cloud instances that do public proxy of all their traffic. And if you get a warrant, it takes you a couple days to go do. Might take longer than that, but it might take weeks or months because they're international. You could probably shut down one of them, and then they just remove it from the rotation. And usually the warrants are to seize them, but it's a cloud server, it's a cloud instance, so like who cares? And if you build encryption technology in them, you can at least be protected against anything except for somebody looking at the memory of the thing while it's running. And the only sensitive data on it is the next hop in the chain. So they build like a multi-level architecture with a bunch of these things. They're not really worried about individual ones being thrown away or being seized. They're worried about the entire system going down. So as long as you can't compromise all of them at the same time, you're pretty good. So the CloudFlare thing we haven't really talked about is we have a bunch of these nodes in like 30 locations around the world, which are like data center cages, so we went the boring route. But we're looking at deploying a lot more nodes than that into places that we trust less. So you see all these areas of the world that are like not included with data centers are places that would be nice to have servers, but you can't really trust putting them there, which is a problem that a lot of companies have. I know Twitter has like 3,000 points of presence or something. I think that's mostly co-located gear with mobile operators, but they have some crazy number of locations. A lot of the CDNs do this thing. Even consumer sites have this problem of like putting stuff out into a lot of places. So there's some basic principles you can do that I think pretty much everybody does. It's sort of best practice. You network boot all the systems from a trustworthy source. You don't really want to keep any data on drives on the machine, both because it gets stale and because they're tempting targets for seizure. You encrypt the contents of memory that are sensitive, so you don't just keep like a key in memory. You keep it in some sort of like white box cryptographic routine, or you don't keep it on the device. You either use the keyless thing that we use, or you use something where You rotate keys. You only have ephemeral keys on the devices. You keep track of all the devices that have a certain key, so that if a device is compromised, you can rotate those keys selectively. TPMs are a foundational technology for a lot of this stuff, so you can do a trusted boot architecture from the machine, so you know that if the machine boots, it's booting from a measured image, and stuff like that, which is pretty interesting and pretty generally applicable. A lot of people could do it, and I know. At least I know Twitter, Facebook, Google do this. I don't know necessarily the whole range of like who uses HSMs versus who uses this versus who uses the like hoping that nothing happens technology. And then there's the open source. So there's Tor and Mixmaster and stuff, which are cool. But I think it would be possible to come up with a way to run a process on servers in a way that has this level of protection, has the hoping that the server is not, or a way to detect if a server is compromised before provisioning it with application-specific keys, and do that as an open source thing. We have some of the stuff that we've done internally that we're open sourcing in the SSL world, so maybe do something like that. And there's the hoping that these new features for Intel and ARM will come out pretty soon. But yeah, if anyone has any questions about this stuff, I would be very interested in talking with people about either the HSM projects or working on maybe some sort of open source way to run software in a bunch of other places. I was just wondering if anyone had any questions or anything at this point. So, cool. And otherwise, we can get on with our drinking. The slides will be on Twitter, so you might want my PGP figure right now. Cool. Drinking. Cool.